that we'll cover for elimination reactions is the E1cb mechanism. So E1cb stands for unimolecular conjugate base elimination reactions. So this typically occurs when you have a carbonyl that has a poor leaving group on the beta carbon. So this is the alpha carbon, the one next to the carbonyl, and then the next one over is the beta carbon. It would have a poor leaving group such as an OH group. Under those situations, if you add base, you can get an E1cb reaction. E1cb reactions are very specific to these types of cases, so they're very rare. We're not going to encounter them too much in this course, but I want you to be aware of them. So the way the reaction occurs is base will remove a hydrogen on the alpha carbon. This is the most acidic hydrogen. And then we would place a negative charge on that carbon as shown here. That negative charge can be resonance stabilized by moving the electrons this way towards the carbonyl to get this other resonance form. Next up, the negative charge would now move to reform the carbonyl, push electrons this way to form the double bond there by eliminating this group. So we would get this as a product. There are a few variations of the details of this reaction where in some places the first step is shown as the rate determining step. In other cases, the last step is shown as the rate determining step. We're going to use this as the way we would describe this reaction, where the first one occurs fairly fast and the last one occurs relatively slow because the leaving group is a poor leaving group. But I have seen under certain situations this being reversed. That same thing goes for the rate equation. I have seen this equation being described as a second order overall reaction. We're going to describe it as a first order, where only the concentration of the alkyl halide is important. And so the rate equation is drawn as rate is equal to a constant times the concentration of the alkyl halide. Here's an example of an E1cb reaction where base will remove this hydrogen, the alpha hydrogen, to put a negative charge here, which then leads to a resonance form that has a negative charge on this oxygen. Then in a second step, we can eliminate the hydroxyl group on the beta carbon, so reforming the carbonyl and then leading eventually to eliminating this leaving group. This second step is usually considered the slow step in the reaction. And we end up with a product that has a double bond between the beta and the alpha carbon next to this carbonyl. Here's an example from a biological system. So again, we have a hydroxyl group on the beta carbon of this carbonyl. If we add base, so a nitrogen could remove this hydrogen on the alpha carbon, we could get the reaction going. And in a second step, the carbonyl will reform by eliminating the hydroxyl group to get a double bond there. Now, in biological systems, you have enzymes which are often chiral. So they can sort of pick and choose which hydrogens to remove. So we see here a hydrogen that is facing back and then a hydrogen is facing forward. Only the one facing back is removed. That is because enzymes are chiral in nature, and so they can sort of react with molecules in a chiral way, removing a particular hydrogen on one side of the molecule versus another.